All right, lesson 8.6. So what do you observe here? So this GIF, there's a bowl and I guess it's a quarter in it, right? That's fastened to the bottom of the bowl, right? And at this point of view right now, you do not see the coin. But once you start pouring water in, something happens, right? For now suddenly once the water is in, you can now see the coin. Why is that, right? Why does that happen? And we did it on the lab. We did it in lab, right? You guys saw that light does in fact bend as it enters another object, right? As it's shown here, you'll see that as it enters the new medium from air to water, your light wave is going to get slower. And because it gets slower, it will bend. Your eye thinks that the image is at a place your eye thinks that coin is at a place that is imaginary. It think your brain interprets it as something that's going straight. But that's not actually the case. And that's not actually the case. And so this is called refraction. Refraction is the change in direction of wave when it passes from one medium to another. And a medium is whatever a wave travels through, right? That's a definition of the medium, right? It could be air, it could be water. Water would be your medium in this case, and then it'd be air on top. So a medium is pretty much anything a wave travels through. And this is always true here. In a wave, you must have an incident ray, you must have a reflected ray, and you must have a refracted ray, right? So all three of these must be true. And this is something important here. So let's say this is air, right? And so this would be water. And so this is the boundary between air and water. Right? This is boundary. And so your normal line, and we want to make sure we draw our normal line. Our normal line is perpendicular to my boundary. Right? Perpendicular. And we know that the angle of incidence is equal to my angle of refraction. Right? So my incident ray is equal to my reflected ray. The angles. And not only must there be a reflected ray, there is a refracted ray. And because you're entering a new medium, well, your light wave gets slower and so it bends. Which is kind of what the GIF on the right is showing. Right. So now we move on to something called the index of refraction. The index of refraction is essentially the speed at which a light wave will move in a certain medium. It's a ratio rather. So index of refraction is represented by the letter N. C represents the speed of light in a vacuum. It's on your reference table, first page, third row. Now I'll bring it up for you guys. So where is it? Grading reference. Let's see if it loads. Ooh, why is it not loading? All right. So third row right here. Third row. Speed of light in a vacuum. 3 times 10 to 8 meters per second. Technically, it is not 3, not exactly 3. We just round it. And v is the speed of light in a particular medium. On the second page of your reference table, you'll see the absolute indices of refraction. They're all listed here for you. Right, so that essentially already gives you the ratio at which speed of light travels in these mediums. So let's move on. So here, and I want you guys to kind of hone in on a singular point here. So light, if you're going from something with a lower refractive index, So air has a refractive index of 1, and let's say this is water. Water has a refractive index of 1.33. So this is water. As light enters, water from air, what happens is that, well, light is going to slow down. Light is going to slow down, and because of that, it's going to curve, it's going to bend. Well, where does it bend, right? How does it bend? Well, you'll notice that the angle here, the incident angle, is greater than the angle here. And you'll see that the kind of light wave kind of bends towards the normal line, right? Kind of bends towards the normal line. Because if an object was going straight, right? If the wave was going straight, it would. Well, let me use a different color. If the wave was just going straight, it would just go this way. But it doesn't. It doesn't go straight. It's slowing down. And when it slows down, it will bend towards the normal line. The angle is smaller than the angle from which it came in. So this is what happens when it goes from a low refractive index to a high refractive index. Your angle decreases and you're moving towards the normal line. Your light slows down. Now the opposite, well, before we get the opposite, let's do a practice question. A light wave is incident from air, right? So it's going from air to flint glass to water back to air. Which part of this picture shows a light wave going from a lower to higher refractive index? And how do you know? There are two ways to solve this. There are two ways. Right, so first way is, well, you can kind of draw a normal line. So again, a normal line is perpendicular to the boundary between both objects, right? So you have air and flint glass. So this is your boundary. So this is 90 degrees, right? You'll see that as air incident angle, as it goes into flint glass, well, your angle decreases and it's kind of bending towards the normal line, right? Because if it would just go straight through, it would continue going this way, but it doesn't. It bends towards the normal line and your angle decreases here. So this means you're slowing down. And this means that you're going from a low refractive index to a higher refractive index. So n here is 1, and that's how we know. So from air to flint glass, we're going from a lower to higher. Another way to tell is, well, on your reference table, it tells you air has an index of 1, flint glass has an index of 1.66. Right? So you can always just look at your reference table and figure out the answer. The opposite is true. If you're going from a high to low, right? If you're going from a higher refractive index to a lower refractive index, then light will speed up. There's not as much opposition to the speed of light, right? Okay, if you kind of draw this incident wave, right? So let's draw the incident wave, and now we have a refracted wave. You'll see that this angle right here is smaller than the angle over here, right? Which means that you're moving away from the normal line. You're bending away from the normal line, and you're getting faster. So this shows you that your wave is getting faster here. Your angle is larger, your refracted angle is larger, and you're bending away from the normal line. It's moving away from the normal line. So that's from high to low, and you're speeding up. So which situation here shows that? So again, you can use your reference table, right? To look at the index of refraction. Which example shows high to low, which is essentially speeding up. Or you can essentially look at it like this, right? So this is your angle of incidence, and this is your refracted angle, and your refracted angle is much larger, right? Your angle is getting larger, and you're bending away from the normal line. And therefore, you are getting faster here, going from glass to water. So you're going from high to low, which makes sense because your reference table says that water has an index of 1.33. And the same thing holds true over here. This looks even more obvious, right? If you draw a normal line, the angle here is smaller than this angle, which means it's bending away from the normal line. So n here is 1. So high to low. So from flint glass to water, it's high to low. From water air, it's high to low. In both of these cases, light is getting faster. Practice problem over here. Which diagram best represents the behavior of a ray from a monochromatic light on an incident, an error incident on a block of crown glass. So again, you're going from monochromatic means a single color. You're going from air to crown glass. Air has a incident index of refraction of 1, and crown glass has incident index of refraction of 1.52. So you're going from a low to high, which means you're getting fat. You're getting slower. So light is getting slower. If light is getting slower, it will bend towards the normal line. It will get a lower angle. So the refracted ray will have a lower angle. This is bending away from the normal line. This doesn't even have a refracted angle, so neither A nor C is correct. This is bending towards the normal line. This is bending towards the normal line. So it's either B or D. Well, we have to figure out, we have to make sure that we know you must have a reflected ray. And a reflected ray will have the same angle as the incident angle, right? So this is your reflected, it bounces off the surface, right? So the answer here is D. B, this is impossible. The reflected ray does not go inside the object. It bounces off. That's what reflected is. Light travels slowest in which one? Light travels slowest in which one? It might be a bit hard to see, but from air to lucite, you're bending towards the normal line. You have a smaller angle, which means you're getting slower here from air to lucite. Not only that, you can just check your reference table for the index of refraction of lucite. And from lucite to medium wide, you're actually, it might be hard to see, but you are bending even more towards the normal line, which you are getting slower from lucite to medium wide. From medium wide to air, you're getting faster because you're bending away from the normal line. All right. So medium wide will be the slowest. Which path will the reflected ray follow in the quartz? So what happens here? I forgot to mention it, but medium X has a index of refraction of 1.46. Fused quartz on your reference table also has an index of refraction of 1.46. So if they both have the same index of refraction, they're gonna keep going through. They're not gonna slow down or speed up. They're gonna go straight through. So it is, answer is here is C. It will neither slow up, speed up, or slow down. Let's take a look at this. So The frequency of wave will be constant. Okay, right. So let's talk about the formula, right? Let's talk about frequency of waves. Now, I told you guys that your speed of a light wave changes. Speed of a light wave changes as it goes through a different medium. And if your frequency changes, well, then that must mean part of this formula, part of your wave of a speed of a wave formula, v is equal to frequency times wavelength, must also change. Well, I'm sorry, I said frequency changes. I'm sorry, I mean speed. Speed changes. So your speed of the wave changes as you go from one medium to another. That must mean one of these values must also change. Well, I'm going to tell you right now that the frequency of your wave does not change. So if your velocity goes up, your velocity of your wave goes up, but that must mean that your wavelength must go up as well. And the velocity of your wave goes down, then your wavelength must also go down. They are directly, v and lambda are directly proportional. They are both on the numerator, right? Now your frequency never changes. The frequency of the wave does not change as you go from one medium to another. As you can see here, light, the frequency of light gives you a color. That's how we know that's how our brain interprets color, based on the frequency of light. Blue and red have different frequencies. Now, visible light, white light, is made up of all those different colors. And because as it goes through a medium like a prism, because the light goes through a prism, the frequencies of each wave slows down. Because each color has a different frequency, they kind of all separate into different colors. They all separate into white light separates into each color that makes up white light, which is what you see happening here. Each of these waves have a different frequency. Because they have a different frequency, they each have a different wavelength and they each have a different velocity, and you see them separately. So let's answer this question. As monochromatic light passes from air to water, two characteristics of the ray that will not change. Again, things that will not change is frequency. Frequency of your wave will never change as you go from one medium to another. So it's either B or D. But frequency and period are inverse of each other. They're inverse of each other. Which means that if frequency stays the same, then t must also be the same, right? Your period must also be the same. Speed will definitely change. Speed definitely changes. So the answer here is B. Speed of your wave changes as you move from one medium to another. 5B. If the speed of wave doubles as it passes from shallow water to deeper water, its wavelength will be what? Again, V and lambda are both directly proportional. So if one goes up, the other must go up as well. So if your speed doubles and your frequency stays the same, well then that must mean your wavelength must also double, right? So they're directly proportional. V and lambda are directly proportional. So this is a formula practice. The formula that was shown is on your reference table. It's beginning of slide. So your index of refraction is equal to your speed of light over your velocity of the light in that medium. So what is the speed of light? In flint glass, you're looking for V, so you're looking for the velocity in a certain medium. You know the speed of light on your reference table. And you know that flint glass has an index of refraction of 1.66. So you're going to use this formula. N is equal to C over V. N is 1.66. Speed of light. V times V times V. 1.66 V divided by 1.66. V gives me something. Well, you guys can figure it out. Use your own calculator, but that's what you should do. Okay? Uh let's do this one. Light travels in air, enters the second medium. Its speed slows to this. So this is your velocity of light in this medium. What is the absolute index of refraction of the second medium? So what was N? So you're gonna use N is equal to C over V. You know your speed of light. Speed of light is 3 times 10 to the 8. V is 1.71. So N is, you guys are gonna calculate yourself, okay? I'm not gonna do that. And that's it.